So we discussed so far we discussed what is stress and its types, and second one is what is strain and its types. Now we are going to discuss another one. Say the subtopic has to be 5, that is Hooke's law. It's a very important one in this topic. Hooke's law. So within the elastic limit, what Hooke's law says, stress is directly proportional to strain, or we can say that the stress by strain has to be constant. So stress by strain, so that is equal to constant. So Young's named that constant has to be generally elastic moduli or elastic constants. So I can say that since these two are proportional relations, so I can draw the graph between stress and strain. So this is strain and this will be stress. Then we see that we are getting directly proportional. So the graph. Many times I said that whenever a graph is given, you have to think about either slope or area. So now you just see that slope of the graph. This is nothing but a strain. Sorry, this is nothing but stress, and this is a strain. So strain. So the slope of sigma versus epsilon. So the slope of sigma versus strain graph, that is a stress strain graph, gives elastic moduli. Will gives the elastic moduli. So we know that the same can be written as slope is nothing but tan theta, that is equal to sigma by epsilon, that is equal to elastic constant E. Yes. So these things you must remember related to the Hooke's law. Now I am going to explain the another topic, stress strain graph for that. So stress strain graph. So just to draw the epsilon is here and this is our sigma. So let us consider that this is the starting point. You just consider a spring. You just load and unload the weight. Suppose you consider this is the thing. So any wire or a spring or something else is there. So just to see that you are adding load in that. So this is loading. That means load means we are increasing the external deforming force. That means the stress increases. According to this law, up to a certain limit, that is known as to be elastic limit. When stress increases, strain in the material also will increase. Therefore, at that point, the graph looks like a straight line. So this is point A. The OA is called proportional limit. And further I am increasing my applied stress, that means deforming force. Then what will happen means the stress also will be slightly increased. Now this, but you just see the graph, the straight line behavior, linear behavior is slightly differ from that. And this corresponding point I can call it as B. This is called elastic limit, and this is called corresponding stress is called yield point, sigma y. So suppose further I am increasing the applied load, then what happens? The graph is surely deviates from its linear proportional variation to non-linear category. So just to see that this is some point C, and further I am increasing that, there is an abrupt change in the graph. So let us consider this is the point D. The corresponding stress for this point D is called ultimate tensile strength. This point, the corresponding stress is called ultimate tensile strength. And further if it increases, they say this is the point E. This point E is called fracture point. Once the applied load is crosses the fracture point, the wire gets break. But you just see that once you reach that, suppose the applied stress is reach the point C, then you just unload that, remove the deforming force. That means reduce the deforming force by removing the loads. Then what we expect is graph should follow the same path, but in practice that will not be like this. The graph will be a straight line, but it will not follow the initial path or initial pattern. So there will be a permanent or non-zero strain. This is say for example O dash. So this is called a permanent set. This is called a permanent set. This value is generally less than 0.01%. And now you see that these regions between C and D is called plastic region. Plastic region. So these graph related problems are there in MCQ exam. If this plastic region is wider, then that material is called ductile materials. That means the material can made as to be a sheet or as if we can fold it like this. So this plastic region is wider, then the material is called ductile. If it is narrower, so narrower, and that is brittle material, it can easily break. So the glass may be the example for this. Any metal sheet which can be make it as to be a sheet, the metal can be said to be as to be ductile, and whose plastic region is more, and the brittle glass which having the narrow plastic region. So this is the important thing what we must consider or is to learn from this stress strain graph. So OA is called proportional limit and B is called elastic limit. Beyond that, the directional property, directly proportional property is deviates from the non-linear, that means from linear to non-linear category. And yes, the next subtopic what we are going to discuss is seventh one. So seventh one what we will discuss means a special type of material. Some material may not follow the such type of behavior, so that is called elastomers. In elastomers, even though there is a change in dimension when we apply the external force, but they cannot follow they are not obey the Hooke's law. So for such type of material, the stress strain graph will be a non-linear one. That type of materials are called as elastomers. Generally rubbers or belongs to that category. Yes. And next what we are going to discuss is a very important core concept of this topic is types of elastic moduli or that elastic constants. Since we discussed three types of stress, one is called lateral or longitudinal, and next one is tangential, and another one is volume. Similarly, we studied four type of strain. One is longitudinal, and next one is shear or tangential, and next one is volume strain. And in this case, the first case of the strain, longitudinal, there are two categories. One case the length may be increases, in another case the diameter or radius of that wire or any cylindrical material can change. So based on that we said that lateral strain and longitudinal strain. Okay. So now the first one is very important one, that is called Young's modulus, which is related to one dimensional property. So y that is equal to sigma is longitudinal divided by s strain longitudinal. This is generally force by area, and this is delta L by L. So just rearrange the term, then we can write that y is equal to FL divided by A into delta L. You just see that we already said there is no unit for strain, and it has the unit for Newton per meter square or Pascal. Therefore, unit of all the elastic constants or elastic modulus are same as to be the stress unit. Okay. Yes. In case of wire, this area can be written as A is equal to pi r square. And next one is you just see the second one is a Poisson ratio. Poisson's ratio. Poisson ratio. So we just taken as to be mu here. In this case, what is this Poisson ratio means? By definition, it is given by lateral strain divided by longitudinal strain. So lateral strain we already discussed that, minus delta R by R, and this is delta L by L. So this is the Poisson ratio. Sometimes some NEET examination the value also asked. So for theoretical value of mu, or this ratio is -1 to between -1 to 1 by 2 for experimental values. For experimental value, that will be between 0 to 1 by 2. So that please keep in mind. The third one is shear modulus. Shear or rigidity modulus. shear or rigidity modulus. Yes. So I can, this is mu and this has to be y. So I can take that as to be eta. That is equal to is a sigma shear divided by epsilon. That is a strain shear. So this is same as to be F by A. But what is the main difference between this F and this F means? I already said that this will be a perpendicular force, but this will be a tangential force to the surface. So F by A divided by F. This strain, we are already said that that has to be shear angle pi, or you can use that is also delta L by L, no problem. So in this case, I can write that eta is equal to F tangent divided by pi A. So this is the rigidity modulus. And for your information, we can compare this shear or rigidity modulus with the Young's modulus. So generally, by comparing these two, we can say that Young's modulus is nearly 3 times of this shear modulus or rigidity modulus. So the third type of that one is, so this is 1, 2, 3 and next one is 4, bulk modulus. Bulk modulus related to 3 dimension. So it is given by B, that is equal to S sigma volume divided by epsilon volume, that is equal to force by area divided by minus delta V by V. And this force by area, since it is acts all the directions perpendicular to the surface, so I can call it as that has to be delta P, that means pressure. So I can write that delta P divided by delta V into V. The negative sign represents that due to this volume stress, there is a change in or reduction in the volume. And again, you just see that I can again divide this has to be a 2 part. One is called the related to this bulk modulus. The one is called compressibility. So compressibility. So that is given as to be K, that is equal to reciprocal of bulk modulus. And second one is very important. Many students are not aware of that. In thermodynamics, we will discuss that there are 2 main thermodynamic processes. One is called adiabatic and another one is isothermal process. So isothermal process. So for example, the proof of this I will give it during the discussion of thermodynamics, but right now I can write that during the adiabatic process there is a change in volume, then we can say that that elastic moduli or elastic constant for adiabatic process is given by E pi, that is given as to be gamma p, and for isothermal that is E theta, that is equal to P. So therefore by dividing this, we know that in thermodynamics we studied that this constant gamma, that is a specific heat ratio S constant, that is given by Cp by Cv. So Cp by Cv, that is you just divide this, so that has to be E pi by E theta. Therefore the specific heat ratio, this constant also can be written in terms of as elastic moduli. This is corresponding to adiabatic process, this is corresponding to as isothermal process, just to keep in mind that. And now the next subheading what I am going to discuss is there is some correlation between these 4 type of elastic constants, that relation. So relation between the elastic constants, okay. So now the first one I can give that, so no other way, you just, there is a lengthy proof for this, but in examination point of view, just memorize that, no issue. So y is equal to 3b into 1 minus 2 mu, and y is equal to 2 eta into 1 plus mu. Please try to understand, this is Poisson ratio, shear modulus or rigidity modulus, Young's modulus, and this will be bulk modulus. And next one is 9 by Sy, that is equal to 3 by eta plus 1 by b, the another relation. And the one more is there, the relation between volume strain and the longitudinal strain. It is also given by 1 minus 2 mu, that is sigma is a longitudinal strain. And you see that when we talk about the shear strain, we said that one end of the wire is fixed and the another end is rotated like this, twisted. So in that case, I can say that torque which is acts on the cylindrical body to twist that wire, this is what is that is a shear torque. I can name that as to be shear torque, that is equal to C into pi. This is what is that tau is like your F equal to kx, like that. So tau is equal to C pi, where pi is, as we said earlier, pi is nothing but is a shear angle. This constant, this is called as a shear torque constant, whose value is given for a wire. This value is given for that wire. So C is equal to some data we must memorize in examination point of view for the quick calculations. So C is equal to pi eta r power 4 divided by 2L, where r is radius of the wire and L will be length of the wire, and eta is shear strain. So now you see that. So these are the important relations. We must memorize it because the proofs are very lengthy and need not to be discussed for MCQ point of view. So please keep that one in mind. And next, what I am going to discuss is some special concept related to this elastic property. Yes, that I can give, that has to be a separate topic. This is subtopic 8 and this has to be 9, and I can classify that has to be 10. Some special discussions. So special concepts are related to this. The first one what I am going to give in that is the first one is thermal effect. So thermal effect on this elastic modulus. So generally, when temperature increases, Young's modulus of the wire will get decreases because of the reduction in the intermolecular force. That concept I will discuss successive topics. Now you see that there is two fixed rigid support. Over there some is a rod of length L is placed. When the temperature, by heating or any other manner, if the temperature of the rod is increases, it is having that tendency, linear expansion will take place. But since these rigid supports are there, which propagate or resist the linear expansion, which develop the stress along the length of the rod, which is called thermal stress. So in this case, you please remember or recall a concept from the thermal expansion. So delta L by L, that is equal to alpha into delta theta. This is the fractional change in length of the rod when it is undergoing a change in temperature, where alpha is called coefficient of linear expansion and delta theta change in temperature. So this is the expression takes place from the thermal expansion. Now you please come to our elastic moduli. We know that strain, that is equal to change in length divided by original length. Since we are talking about effect of temperature, so I can call it as this has to be thermal strain. So epsilon TH, that is delta L by L, that is equal to alpha into delta theta. And since these edges are fixed, it is trying to expand, but this rigid support will oppose that expansion. Because of that, some internal force is developed in the opposite direction. So which is responsible for the thermal stress. So therefore, I can write that thermal stress sigma TH, that is equal to, generally we know that Young's modulus is equal to sigma by epsilon. So therefore, from this I can write that sigma is equal to y into epsilon. So y into thermal strain. So that is equal to, so y is there alpha. So y into alpha into delta theta. So this is the thing what we must know related to thermal effect. The another one is called free expansion, free thermal expansion. That also very important. Suppose the same way, just consider a rod of length L, but whose one end is fixed rigidly and another end is not fixed rigidly. So when the temperature increases, the length will change, but that is not because that will not produce any internal restoring force. And such type of cases, this where there is a change in dimension, but there is no restoring force developed in that. Such type of expansion is called free expansion. Such type of expansion is called free expansion. So free expansion of the material. So in this case, even though length will be changed, we cannot say by definition delta L by L has to be as epsilon or strain, because in this case, even though the length will change, that will not produce any restoring force in that system. That's why for a free expansion, the thermal strain will be zero. Thermal strain will be zero, and that is the main thing what we is consider in this case. And second one is, second concept is there. I'm not going to discuss the derivation. That is called intermolecular force constant. So intermolecular force constant. Yes, you just see that a wire can be treated as a spring. So by you just see that, and this is the wire of length L. Due to some external deforming force, the length will be as changed as to be delta L, and this is the external force F. So I can say, or we can treat this wire as to be equivalent spring system. So this is like this. This is the external force F, and the change in length is taken as to be delta X as to be delta L here. Then I can say that spring constant of this material K is equal to F by delta L. So similarly here also I can write that is F by delta L from the Young's modulus. We know that what is Young's modulus here. So Young's modulus we know that. So Young's modulus Y is equal to FL divided by A into delta L. You just take this F by A delta L alone, that has to be K. Therefore I can write that K is equal to, this term is K, and cross multiply that, K is equal to YA by L. And this is the another important relation which is very useful to solve the problems which consider the rod is equivalent to a spring of spring constant K is equal to YA by L. So in this same manner, this is called a spring constant of the given wire. But in the actual spring case, there we said K is equal to F by delta L or delta X. But by comparing these two analogy between the rod and the spring constant of the rod is given by, or wire is given by, K is equal to YA by L. In the same manner, the intermolecular force constant, I can directly give that. There is a little bit lengthy derivation. I can give that for intermolecular as a force constant, that is given by R naught into Y, where R naught is called intermolecular distance. Intermolecular distance at equilibrium, or simply called equilibrium distance, and this is Young's modulus. So right now the theory part, second part of the theory is over. So kindly note it down. So the last what we discussed is intermolecular strain is the force constant which produce the which is due to the intermolecular force. Now we see that the origin of the category or types of the materials mainly depends on the intermolecular force. Why some substances are solid, why some substances are liquid state and gaseous state. So generally, since examination point of view I am discussing, first I am giving the core concept, then I am going to the less significant topics. So let us consider any solid material which is made up of either atoms or molecule, and just we consider, and these are the two atoms which are analogy or compared to be a bond formation, which is generally assumed as to be a elastic spring. So this is just like this. This is molecule 1 and molecule 2, and there is a attraction or repulsion depends on the their equilibrium separation. Now you please see that I can draw the a graph between the intermolecular distance and the potential energy. Now we see that, and now we see that whenever the potential energy of the system, there will be a repulsion, and when there is a negative energy for the potential energy and negative sign, then we can get the attraction. So therefore the graph for potential energy graph is given by like this. There is a minimum potential energy which correspond to a distance, intermolecular distance R0, that is called equilibrium distance. When the separation between the two molecules is more than or greater than R0, the attractive force will be reduces, but that will be still in the negative region, so attraction will be there, but the value will be reduces. But when the intermolecular force is less than the R0, the energy, potential energy of the system is increases towards the positive value. So therefore this region is related to repulsion, and this will be responsible or region for the attraction. So there is a relation, and how that repulsive force between the atoms or molecules or attractive force between the atoms or molecules will change. Therefore the net intermolecular force between the molecules or atoms, which can be splitted as a two category. One is attractive force and another one is repulsive force. So in this case I can write the attractive force is very like A divided by minus A divided by R power 7, whereas B, this has to be R power 9. These are all the empirical formula or the thing what we assume to be from the theory. And why then there is a negative sign which is responsible for attractive force and repulsion positive sign. But you see that in what manner these two forces are vary. F attractive is inversely proportional to R power 7, but here it will be repulsion is R power 9. And when you move away from this what is that equilibrium position, that value of repulsion will be play the major role, and which is responsible for the change of state by changing the net intermolecular forces. Now also we know that F is equal to, in mechanics we studied that F is equal to minus du by dr, and for equilibrium category we know that F will be 0, which gives the equilibrium distance or R0 value. So this is a very brief idea about what is intermolecular force and how it is depends on the potential energy. By this expression I can draw the graph for this also, but the graph is very similar to this. You just replace the potential energy axis, that's all. So, and this is a very special theory and what we consider. And another thing what we said there in the last lectures or the last part of the discussion is we just see that a rod can be considered as a or equivalent as a spring whose spring constant is given by K is equal to YA by L. For the given wire, Y is constant. If the given wire is uniform, then A also constant. Therefore YA is constant. Therefore I can write that KL equal to constant. This equation is very important when we discuss about oscillation lesson, because there is a combination of the spring, that means a series and parallel. So I can give the brief idea here also. So now you see that for series combination of the wire or parallel beams or that one, you just see that series combination. For a series combination, you just consider these are the two wires of made by different materials. Just now we assume that a rod is equivalent to a spring of a spring constant value this. Therefore, this is 1 and 2. This can be easily understood or deal with spring analogy. So now you see that this is the first wire of a spring constant K1, and this is the another wire of a spring constant K2. So therefore, in series combination, F is same, but the extension delta L will be different. So therefore, I can write this K as equivalent springs constant of the system 1 by Ks, that is equal to 1 by K1 plus 1 by K2, or I can write that Ks is equal to K1 K2 divided by K1 plus K2. So similarly, if the bars are connected parallelly, and that can be given as to be like this. Suppose this is the rigid support and this will be the another one. The two rods are given in this manner. Yes, this type of problem is easy to solve even for JEE problem also. Now some external forces acts on this. Say this is material of rod 1 and this is rod 2, and this is treated as to be in this manner. So this is spring 1 and this will be spring 2, whose spring constant value can be written as K1 is equal to Y1 A1 by L1, like that. So in parallel combination, just to see that here just opposite, force is same, delta L extension is different, but here F will be different, but delta L is the same here. So in this part we can say that this force acts on that one is F1 and this has to be F2. So this is some external force, deforming force W. Therefore in this case the equivalent spring constant of the given rod K parallel, that is equal to K1 plus K2 etc. so on. So this is the very important thing which can simplify our problem solving method by considering rod as to be is equivalent spring. The next topic what we consider is energy, or simply I call it as energy, or here we call it as elastic energy. So elastic energy or elastic potential energy, that is the suitable term. So whenever some external forces acts on the body, there is a change in intermolecular distance between the atoms or molecules, which produce the potential energy of the system. So the work done required to change the intermolecular distance, or to change the, in macroscopic point of view, you can say that has to be change in dimension. That is given by general definition for work done is F average into displacement. So force into displacement. So that is here F average is given by F by 2. So that is F by 2 into delta L. So this is the very general expression. What you must keep in mind that of F into delta L. This is very important thing we must keep in mind. By using this we can get the many other forms of this relation for this. For example, I am multiplying by volume and divided by the volume. The same equation, this is the original equation. For in this same equation, if I am multiplying by the volume and divided by the volume, and this volume is nothing but the area into length in case of wire, then you just see that the equation, or I can get the another form of this general expression. So U is equal to 1 by 2 F into delta L into volume is there. So divided by area into length. We just see this expression, children. F by A is nothing but is stress, and delta L by L is nothing but strain. Therefore, simply I can write that W is equal to U, that is of, this will be stress, this will be strain, and this is your volume. So volume, energy by volume is called energy density. So energy density. So small u, that is equal to energy by volume. Just to take this denominator, the remaining term what is there means of into sigma epsilon, that is stress into strain. So this is the expression. If you want any other format in terms of Young's modulus, or in terms of only stress or only strain, you just modify this original expression by doing this expression, or by using this expression y is equal to F by A divided by delta L by L. You can use any expression to modify this original equation. And based on this, I can draw the graph, because we already discussed that what is a stress strain graph. just see that this is the stress strain graph. So what we discussed in Hooke's law, sigma. Now you see that, you just see, yes, many times I said that whenever a graph is given, you have to think about two things. One is about the area and another one is about the slope. The slope of the graph we already discussed in Hooke's law. The slope of the graphs gives the elastic constant. Here the area. For example, you just consider this is the given thing and you assume that this is passing through the origin. Yes, okay, yeah. So now you see that the area under this curve, area under this sigma versus epsilon curve, this is area. So therefore area is nothing but triangular shape half into base into that is epsilon into sigma, that is stress into strain into stress. Just to see this equation, yes, or this is the energy density formula what we highlighted here. This is the energy density formula. So that is 1 by 2 sigma E and 1 by 2 sigma E. Therefore, what is the conclusion of this graphical discussion is area of sigma versus epsilon gives energy density, that is small u, energy density, whereas the slope of the graph, slope of the sigma versus graph gives the elastic constant, constant. So these are the main thing what we consider here. And next, the last topic what I am going to discuss is so the practical application, the practical applications of elasticity or elastic property, elasticity. So the first one, you just see that we saw many weightlifting machines where the very big and steel ropes are used. So that what is the maximum capacity or what should be the minimum radius of the wire or the rope to lift the certain load weight. Okay, so we know that sigma is equal to force by area, or from the force is nothing but here the load what or the mass what we are going to lift, or this can be written as mg divided by area. So from this I can write that the minimum area of cross section of the wire which is used to lift the, or a crane rope which is used to lift the mass, A is greater than or equal to mg divided by sigma. I just modify this equation. So this is the essential condition to select the suitable diameter of the rope to lift the given object or mass, anything which is generally used in engineering purpose. And the second application is, and the second one. So second one is just to see that many constructions, all these things, properties of solid is mainly used in construction of heavy machines or construction of bridges like that. Just to consider a rectangular, bar. Yes, when you apply the external load at the middle, what will happen means there is a change in shape of this. So it will be changed like this. There is a slight bend in this. Yes. So so now you see that this displacement is generally called delta, and this effect is called buckling effect due to the external load acts on this. So acts applied to this. So this will be external load act on this system, or W. So this delta is given by delta is equal to WL cube divided by 4BD cube Y, where L is length of the rod and B is breadth and D is thickness of that, and Y is called Young's modulus. And this is the calculation which is used, how much load the pillar can sustain or can bear with that. So most of the cases, engineering purpose, they are using I-shape pillars to reduce this delta effect or which can bear the very large loads. And the third one is why the mountains are, we know that the very highest mountain is Everest, but why it is not exceeding certain limit of values around that is not beyond 11 or 12 kilometers. The main reason behind this concept over the maximum height of the mountain also is related to a mechanical properties of solid. You just consider when the mountain is due to that as a molten state of material, the mountain is raised like this. But once the certain height is increases, the own weight acts on this lower part of the mountain, will make the shear stress. So because of that, there is a sliding effect on this at the basis of the mountain, which reduce the or which control the height of the mountain. So that can be given by the shear stress. Sigma is given by h rho g, where h is the maximum height of the mountain and rho is the density of the material, and g is, we know that, acceleration due to gravity. So this is the special thing or the things what we discussed so far, and just to revise the theory, and which can give you the better understanding of the concept. And in the next lecture we can discuss the numerical part with the different types.